So hello everybody, how are you all? I hope you all are fine and safe. So today again I just came back with another interesting video, and in this video what we are going to discuss is, I'll tell you in a while. But before everything else, let me tell you sorry because I haven't been continuous on YouTube or interacting with you. So I'm sorry about that. But it's alright. And now in this video, this is gonna be an epic video, right? And because we are going to discover or we are going to discuss about this guy or this guy's work, that is, so this is what it is. And I hope you guys have boosted your curiosity after just looking at the name of this guy, that is Srinivasa Ramanujan, right? And that is what we are going to work in this video, because we are going to discuss in an infinite product from Ramanujan's lost notebook, right? Okay, so this is gonna be an epic video. Please, I request you, and I request you to just watch this video till the end without any kind of break, because then only you could be able to understand everything what I'm just going to explain in this video, right? But before everything else, I just got up this product from Michael Penn. He's a renowned mathematics video maker or presenter on YouTube. He's very famous, and I would request you to please just check out his channel too, because yeah. But why I'm going to explain it again as he did it in his video. So instead of just recommending you to just watch his video, why I'm just telling you to watch my video, because I'm just going to explain the same stuff that he did. But the way he explained is quite difficult to understand. Most of you maybe are not able to understand what he just taught. Even I was surprised. I took almost 3 to 4 hours to understand full video. Not 3 to 4 hours, but yeah, it was around 1 to 2 hours, right? So, and for for better understanding, I'm just going to explain you each and every step that Michael Penn didn't explain. Maybe there is a reason why he did that, because he just wanted us to try out or imagine out how could it be done, right? That's how, and that's why he is PhD in mathematics from Ivy League. Okay, instead of talking about him, let's just get into our video. So what we are going to just discuss is, I'm just writing it over here. That is, let's say that this product is P. So P equals n equals 0 to infinity of 1 plus 4 upon 2 plus 1 to the 4 times minus, no, it's to the power, actually I hope you understand that. The product from n equals 0 to infinity of 1 plus 4 upon 2 plus 1 whole to the 4th and whole to the power -1 to the n times 2n plus 1. So yeah, this is the product that we are going to evaluate along with explanations of Michael Penn. Okay, so this is what we are going to evaluate, and this is going to take a lot of time to be evaluated, because this I'm not sure that this is looking quite simple, because this looks evil for some viewers like me at first glance. Even though we have to do that, we don't care about the looks, we have to care about the solution, right? Okay, so let me write firstly that where did Michael Penn got this? Ramanujan's lost notebook, right? So he just got up this product from Ramanujan's lost notebook, and now we are going to evaluate this. But before everything else, I would like to just write some few tools that we are going to use in this video. And for that, let me just fill up my black marker as I think it's dry. Okay. So yeah. So like we would be needing some tools to just evaluate this, because this isn't looks that simple to be evaluated as, yeah, it's an factorial or something like that, but it's not like that. So what we are going to use it, I'm just writing it down over here. Tools, right? So first is the hyperbolic secant x is 4 pi times the product as n goes from what, 0 to infinity, of negative 1 to the n times 2n plus 1 over 2n plus 1 pi, 2n plus 1 square pi square and plus 4x square. I hope you guys can see all the stuff that I wrote here. Let me explain you again. So it's the hyperbolic secant x that is being represented in an infinite series. That is 4 pi times the product, the series as n goes from 0 to infinity of negative 1 to the n times 2n plus 1 upon 2n plus 1 whole square times pi squared plus 4x square. That's it. Right? And another tool is, I think I should just I need more space. Yeah. So yeah, this is second, and this is third, and this is first. So let's talk about first. That is arctangent of I times e to the negative pi over 2 can be represented as I over 2 times ln of 1 minus e to the minus pi over 2, 1 upon 1 plus e to the minus pi over 2, right? And the third one is log of z equals ln of modulus of z, that is the absolute value of z, plus I times the argument of z. So these three things we are going to begin with this one, and we will use these two things later in the video, right? So I think we should begin right away. Okay. So now, first of all, let's assume an arbitrary infinite series, right? Let's assume. So I'm just saying that, let's say that s of x, right? The arbitrary infinite series is s of x, right? So s of x is the series as n goes from 0 to infinity of negative 1 to the n times 2n plus 1 and times log of 1 plus lambda x squared over 2n plus 1 whole square. Okay, so at first let me just sort out this quite bit. So x belongs to 0 to infinity and lambda belongs to a complex number or complex part, right? So that is what we are going to deal with, we are going to begin with, right? So that is what. Okay, so the next step is we are going to take the derivative of this s of x, right, with respect to x, obviously. So the derivative of s of x is the same as the infinite series as n goes from 0 to infinity. Because these two things are constant, so if they are being multiplied to the terms which includes x, so they are not going to be factored, or no, they are not going to be differentiate, right? So they are just going to be written like as they were. So yeah, and now we are going to use the chain rule for this part to be differentiated. I'm talking about this part, right? Okay, so if we talk about the chain rule, then look closely. Let me tell you. So what I'm talking about, taking the derivative of log of 1 plus lambda x squared over 2n plus 1 whole square, right? So using chain rule, then taking the derivative of 1 plus lambda x squared over 2n plus 1 whole square plus taking the derivative of, no, it's not plus but it's times the derivative of log of 1 plus lambda x squared over 2n plus 1 whole square, right? Okay, so this becomes the derivative of 1 is 0, and this becomes the derivative of this part is 2 times lambda times x over 2n plus 1 whole squared, and times the derivative of this thing is log and an argument, right? And we don't need to take the derivative again. So because we took the derivative of the internal part or the argument inside the logarithm, right? So that is going to be just 1 over 1 plus lambda x squared over 2n plus 1 whole squared. Or more precisely, you can say that let's multiply the this 2n plus 1 whole squared into this this parenthesis, right? So we are having 2 lambda x in the numerator, and in the denominator we are having 2n plus 1 whole squared plus lambda x squared. So that is what the derivative of this thing is, it comes out to be, right? So that is what we are going to write over here. So it's 2 lambda x over 2n plus 1 whole squared plus lambda x squared, right? So I hope till now, guys, everything is clear to you, because I haven't did a lot of I haven't did quite difficult things, because it's quite easy to understand, right? Okay, and now let's move on to the next part. We have successfully took the derivative of the part that we assumed to be differentiated, right? And now our next part is, okay, so here I would like to just multiply with pi squared and divide with pi squared. We can do that. It's our authority, right? Okay. So so the derivative of s of x equals the sum, or maybe I should write it, I should just take some constants out of the series. That is, I can take I can take these two things, right? So it's 2 pi squared lambda x times the series as n goes from 0 to infinity of negative 1 to the n times 2n plus 1 over 2n plus 1 whole squared pi squared. Remember, guys, I just took this pi squared out of this, I just took this term out of this infinite series, but I just multiplied this pi squared into these two things, right? So they are going to look like something lambda x squared pi squared. Okay, and now again I'm just going to do something. I'm just going to multiply and divide with 4 pi outside this infinite series. So this becomes d over dx of s of x 2 pi squared lambda x over 4 pi times 4 pi everything is being copied out, right, as it was earlier. So yeah, and now here we are going to do something. I'm just going to do like this: 4 times x pi square root of lambda over 2 whole square. Let me just explain you, because most of you may be finding it quite difficult to digest that. Okay, why I did? We can just let's square this. So this is going to be x squared times pi squared times lambda over 4. 4 and 4 getting cancelled out, we are going to have the same stuff that we have earlier, right? And yeah, and here we did just 4 pi and 4 pi, like divide and multiply with each other. And why I'm doing all the stuffs, because I just want to represent, or I just want to make like to comparable these two things, the hyperbolic secant x and that the derivative of s of x. That's why I'm doing that. And I'm pretty sure, like I'm pretty close about that, right? So the derivative of s of x is solve this thing. So this becomes pi lambda x over 2, right? It's 2, and times 4 pi, the infinite series as n goes from 0 to infinity of negative 1 to the n 2n plus 1 over 2n plus 1 whole square times pi squared plus 4 pi x square root of lambda over 2 whole squared, right? Okay, and if you look closely, guys, then let me just explain you right over here. Let's assume the hyperbolic secant x is 4 pi, this infinite series negative 1 to the n times 2n plus 1 over 2n plus 1 whole square times pi squared plus 4x squared. And if I'm replacing x with what I had here, pi times x times the square root of lambda over 2. So it's pi times x times the square root of lambda over 2. Then our argument of hyperbolic secant becomes pi x square root of lambda over 2. And this becomes 4 pi, the infinite series of negative 1 to the n times 2n plus 1 over 2n plus 1 whole squared pi squared and 4 x times pi times the square root of lambda over 2 whole squared. Maybe if your eyes are perfectly natural, because I'm not having a perfect natural eye, then you can probably have guessed out, because we have successfully derived this same stuff that we have here, right? So now we can successfully like replace this whole big infinite series with that a small like argument, that is secant of pi times x times the square root of lambda over 2. Hyperbolic secant, sorry guys. Okay, so our d by dx of s of x becomes this pi times lambda times x over 2 and times hyperbolic secant of pi x square root of lambda over 2. So we are having a perfect or a quite good looking result till now. And now we are going to just erase this stuff and we'll continue over this board. Okay. And now I'm just going to integrate both sides to get s of x with some integral. So integrating both sides, like let me try it over here. Oh, let me check, guys. All the videos are just running perfectly. Yeah, the video is running perfectly correctly. So right, integrating both sides, right? So if we integrate this, or taking the antiderivative. So if we take the antiderivative of this stuff, we are going to have just s of x, and on the right hand side we are going to have pi times lambda over 2 times the integral from 0 to x of t, and hyperbolic of pi times wait a second, guys. Okay. Was it square root? Let me check. Oh, sorry. I thought there was a square root of on square root of x that is going to be replaced with t, but the square root is on the square like lambda. Thank God. So yeah, pi times the square root of lambda times t over 2 dt. So yeah, this is what we have to integrate to get s of x, right? And how we're gonna do that? But before that, before looking at this hyperbolic secant, let me just evaluate, or let me just convert this into like Euler's expression, right? So I hope you guys have an idea about the hyperbolic cosine of z equals e to the, I think it's z plus e to the minus z over 2, right? Let me check it, even I'm not sure about that, but yeah, this is what. So if we just switch up like taking the reciprocals, so this becomes hyperbolic secant of z, and this becomes 2 over e to the z plus e to the negative z. And let's replace z with the argument inside this hyperbolic secant x, that is pi times the square root of lambda times t over 2. So this becomes hyperbolic secant of pi times the square root of lambda times t over 2. And this becomes, let's just replace all these z's with this argument only, right? So this becomes e to the pi times the square root of lambda times t over 2 plus e to the negative pi times the square root of lambda t over 2. So yeah, we have a perfect relation between the hyperbolic secant of this argument and e terms. So now we can replace it with now we can replace this with all these stuffs to get our life easier, because this looks very disgusting, I think. So let's just talk about this thing. So s of x becomes pi times lambda over 2 times the integral from 0 to x of t as earlier, and times 2 over, or let's erase this, e to the pi times the square root of lambda t over 2 and plus e to the negative pi times the square root of lambda t over 2. Okay, and now dt, don't forget about that, right? Okay, so and now I'm just we can cancel out these twos, right? And now I'm just going to multiply and divide with e to the negative pi times the square root of lambda t over 2. So s of x becomes pi lambda integral from 0 to x t times e to the negative pi times the square root of lambda t over 2, and in the denominator we are having, if I multiply this argument with this, it becomes 1, right? So this becomes 1 plus e to the, and if I multiply this argument with this, so it becomes 2 times. So 2 times of this argument becomes that, like this becomes minus pi the square root of lambda t dt. Guys, I hope till now everything is being understood by you, because yeah, it's quite easy to understand. I haven't done a lot like difficult things. I just multiplied and divided with e to the negative pi times the square root of lambda times t over 2. And now let's make our life quite easier. So let's erase the stuff on the right board. And again guys, if you are having any sort of doubt, you are free to ask in comment section, and I usually mention it in my description box. So yeah, okay, so we are having s of x as pi times lambda times the integral from 0 to x of t times e to the negative square root negative pi square root of t lambda times t over 2 over 1 plus e to the negative pi square root of lambda t dt. Okay, and now this integral is quite manipulative. Okay, right. So now what I'm going to, like, how I'm going to integrate this. Actually, if I'm talking about the Michael Pence video, so more specifically I got struck on this integral part only, mostly, but yeah, it's quite difficult or quite manipulative to evaluate, but it's all right, I'm here to evaluate it. Okay, so our first step is let t equals minus m over pi times the square root of lambda. I don't need to keep that down. So dt becomes minus dm over pi times the square root of lambda, right? And if we talk about the limits, so we can just replace it with our mind given. We don't need to write that. So s of x becomes pi times lambda. When you plug 0 on the place of t, m becomes 0. And when you plug x, so this becomes minus pi x square root of lambda, right? Please check that out, guys. If you check that out, if you're having any sort of problem with that. So t is being replaced with minus m over pi times the square root of lambda, and this e to the negative square root of lambda over 2 times t. So t is being replaced with this. So if we look closely, then this pi times the square root of lambda and this pi times the square root of lambda is being cancelled out, and we are just having e to the m over 2, because negative and negative becomes positive. And in the denominator we are having again the same stuff, 1 plus e to the m, but this was m because it's 2 times of this argument, right? And this becomes minus dm over pi times the square root of lambda, right? And yeah, so s of x becomes this square root of lambda times this square root of lambda is lambda. So this and this and this becomes cancelled out, and this pi and this pi become cancelled out, and we are having another pi with 1 over pi outside integral, and the integral from 0 to minus pi times x times the square root of lambda. And this minus and this minus, my minus times minus is positive, so we are having m times e to the m over 2 over 1 plus e to the m dm, right? Okay, so from this ridiculously looking integral, we have converted this into a quite relaxing looking integral, right? And our next journey begins. Again, a use of, that is, let's talk about when m over 2 becomes n. So here m is 2n, right? And the dm is 2dm. So s of x becomes 1 over pi integral from 0 to, when you just plug this over there, so n becomes half of this thing, that is negative pi times x times the square root of lambda over 2. Don't worry guys, I'll write this down again on this board for your convenience, because maybe you are not having a proper like vision of this thing that I just wrote here, but it's all right, I'll write it down again. And m becomes 2n, so 2n times this e to the m over 2 becomes e to the n over 1 plus e to the 2n, right? Because m is 2n, right? So this m becomes e to the 2n, and so and dm was 2 times dm. Okay, let me just write it down again over here. I hope guys everything is being understood by you so far, so clear, because yeah, it's quite quite good. So yeah, let me just repeat that again. So s of x is 1 over pi times the integral from 0 to minus pi x square root of lambda over 2 times 2m, sorry it's n, and e to the n times over 1 plus e to the 2n, and this becomes 2dn. So s of x becomes 2 times 2 comes out of the integral, so 4 over pi times the integral from 0 to negative pi x square root of lambda over 2, and this becomes n times e to the n over 1 plus e to the 2n dn. Okay, and now what we are going to do is, let's say e to the n equals z. Another last, I think it's, let e to the n equals z. So this implies that e to the n dn is also dz. It means dn is dz over z, right? So s of x becomes 4 over pi times the integral from 0 to negative pi x square root of lambda over 2. N becomes like, n is ln of z, right? Be mindful of that, right? Yeah. So n becomes ln of z times e to the n was z over 1 plus it's e to the n whole squared, so it's 1 plus z squared, and we have dz over z. Just we got rid of this, and we are just having 4 over pi times the integral from 0 to negative pi x square root of lambda over 2 of ln z over 1 plus z squared dz. I think there is another use of, I think, yep. Let me just take it down. Oh, wait a second. No. Limits. Oh my god. Limits. I was blundering, I think. Okay. So limits are gonna this argument with e in the power. So this becomes e to the negative pi x square root of lambda over 2, e to the negative pi x square root of lambda over 2. So this is the limit, right? Let me just check it down. And again, there is another mistake that I did. Limits. So it is going from 1 to e to the negative pi times x times the square root of lambda over 2. Check it down. Just put n equals 0 over here, so z becomes 1. And when you plug n equals this argument, so z becomes e to this argument, right? So yeah, now it's correct, right? Okay. And now we are not going to use u sub, but we are going to use by parts, or maybe more precisely, I'm going to use my preferable method, that is DI method, to use by parts, right? So the DI method is for this integral, that is s of x equals 4 over pi times the integral from 0 to e to the negative pi x square root of lambda over 2 of ln of z over 1 plus z squared dz. So using the I method, that is plus minus, taking the derivative of ln of z obviously, and the integral of 1 over 1 plus z squared. So this is the arc tangent of z, and this is 1 over z. This times that, and this is inside an integral. So our s of x becomes 4 over pi times ln of z times the arc tangent of z. This is being evaluated from 1, no, it's not from 0, but it's from 1. to e to the minus pi x square root of lambda over 2, like the limits, right guys, like the limits, the only limits, and with a negative, the integral from 0, no, from 1 to e to the negative pi x square root of lambda over 2 arctangent of z over z. Don't worry about this integral guys, because this is going to be vanished, because this is a purely imaginary like unit, or purely imaginary integral, and we're not talking about imaginary parts. We will take the real part of this s of x, so obviously this is going to be vanished because we are talking the real part of s of x, right? But not now. So yeah, okay, so here is 4 over pi, right? Yeah, let's just plug the values in this part. Look guys, when I plug like z equals 1, so this becomes 0, it means tangent inverse of argument is also 0. And when I plug this wait a second, okay, yeah, and when I plug this thing, so this becomes s of x equals 4 over pi times ln of this part is just negative pi x square root of lambda over 2, because I hope you guys understood what I'm talking about. It's ln of e to the negative pi x square root of lambda over 2. So this argument just comes out in the front and this becomes 1. That's why I just wrote it down directly. Times arctangent of e to the negative pi x square root of lambda over 2. And minus 4 over pi, the integral, well, we don't care about that, but it's alright, let me write it down. E to the something and arctangent of z over z dz. Okay. So yeah, this is what, but mainly we will be focusing on this part only, because we don't care about that, as I said. So yeah. So this, now we are going to just continue our process with yeah, okay, and now just multiplying this 4 over pi argument inside this. So well, obviously this is cancelled out and this is, yeah, so this becomes that. So finally we are having s of x equals minus 2 times, obviously root minus 1 times 2, it's minus 2, and times x times the square root of lambda, that is minus 2 times square root of lambda times x, and arctangent of e to the negative pi x square root of lambda over 2, and then we are having minus 4 over pi integral from 0 to e to the something of arctangent of z over z dz. Okay. Well, I'm sorry guys, we care about this integral. Oh my god, again I did a blunder. Like, I'm just messing up with the limits. Sorry, again sorry guys. So yeah, we are just going to extract something out of this integral, and then we will just like, okay, what I'm talking about, let me just write it down clearly and then I'll talk about it. So it's minus 4 over pi integral from 1 to e to the negative pi x square root of lambda over 2 of arctangent of z over z dz. Well, to be noted guys, I can write this integral into 2 parts. And how so? Let me just explain you right over here. So this becomes, let's take out minus 4 over pi. So this is something like this. Integral from 0 to e to the negative pi x square root of lambda over 2 of tangent inverse or arctangent of dz, and minus the integral from 0 to 1. If I subtract this from this, then I'm having the same result, right? Like look, let's imagine this is 0, like this is 0 and 1, right? And this part is 1 to that power, right? This. So if I'm taking this to that, like 0 to that power, and then I'm subtracting it with 0 to 1, so I'm having the same thing that we are ought to, like yeah, this is what we're having. So yeah, we can do that. So this becomes arc tangent of z over z dz. Okay. I'm not talking about this thing, I'm not talking about this integral, but this integral, guys, is Catalan's constant. And if you want a separate video to be proven, like how this equals a Catalan's constant, that is z, actually g. So please comment, please write it down in the comment section. I'll just bring it up for you. So finally, like this whole thing comes out to be 4z over pi, 4z over pi, right? This g. So yeah, and minus 4 over pi integral from 0 to e to the minus pi x square root of lambda over 2 of arc tangent of. So yeah, so this is what we're going to copy it down over there. Let me just write it down. So yeah, what we're having is s of x minus 2 times the square root of lambda x arc tangent of this argument e to the negative pi times x times the square root of lambda over 2 and plus 4g over pi and minus 4 over pi times the integral from 0 to e to the negative pi x square root of lambda over 2 of arc tangent of z over z dz. Okay, and now we are going to just replace x and lambda with some assumption, like obviously inside the domain of them. So let's say that x equals half and lambda equals 8i. So I hope you guys have an idea about how to find the square root of a complex number. So the square root of lambda becomes 2 times 1 plus I. And if you're not familiar with how we can prove this, so please again write it down in the comment section. I'll bring it up for you again, another separate video in which we can practice some questions, because it's quite necessary, right? So yeah, now plugging all these three stuffs inside our expression, so this becomes s of half equals minus 2 times the square root of lambda is 2 times 1 plus I, and x is half, right? And arc tangent becomes e to the negative pi times x is 1 half, actually half, sorry, and square root of lambda is 2 times 1 plus I and plus 4z over pi minus imaginary. Let's write this as image, something like that, imaginary part, because I'm not gonna just copy down again and again. So yeah, let's simplify this stuffs. So this becomes s of half. This and this we can cancel out, and minus 2 times 1 plus I times arc tangent of e to the this is getting cancelled out, so this becomes minus it's like e to the minus pi times 1 plus I. And I will tell you how to calculate this using Euler's formula. Okay, let me tell you guys, recently I uploaded the Euler's formula proof, and the Euler's formula is this, guys. If you haven't been checked out, please check it out because it's very important. So I have uploaded it on YouTube, the proof of this formula. So please just check that out if you haven't been. And yeah, we are having 4z over pi minus, again image. Yeah, so far so good. And now we are going to just mainly focus on this argument to be solved, because we have two things to be used. We have used this earlier, but we have two things to be used, and this one is going to be used just after, I think, that board, on that board. But firstly, let me just solve this for you guys, right? And now we are just going to solve this. We are going to solve the argument of the arc tangent, that is e to the minus I pi times 1 plus I. Open it up, so this becomes minus pi times e to the minus I pi, right? Well, there is a very fascinating and the most beautiful equation in mathematics, the Euler's identity, that says e to the I pi is -1. So if I'm taking the reciprocal of these two things, so this becomes e to the minus I pi is also -1. It means that this is -1. So this becomes e to the, wait a second. Am I doing everything correctly? Let me just check it down. Wait a second, guys. Yeah, I think, yeah, it's going fine. Did I miss something? Okay, let's go with that. I think I haven't missed anything, because this is x half and the square root. Oh my god. Oh, wait a second. Yeah, that's good. Okay, yeah. So yeah, let's solve it. Yeah. Oh my god. So this becomes minus of e to the minus pi. Okay. And now how are we going to do that? E to the pi. Am I doing everything correctly, you guys? Please let me know that I have did everything correctly, because I am having some sort of problem while evaluating this. E to the, wait a second. Oh my god, I missed something. I'm sorry, guys. There was 2 in the denominator rather than these two things. So yeah, that is what I was missing with. So this was 2, 2 and 2. Yeah. Let's not talk about this Euler's formula or Euler's identity. But yeah. So if we talk about e to the I z equals cosine of z plus I times sine of z, and if we replace it with minus pi over 2, so this becomes e to the minus I pi over 2, that is this thing. So cosine of minus pi over 2 plus I times sine of minus pi over 2. So this becomes 0, and we are having e to the minus I pi over 2 as this becomes negative I, right? So we are successfully having this equals I times e to the negative pi over 2, right? So that's what I meant to like make you understand about. So this is I times e to the minus pi over 2. So our s of half becomes 4z over pi minus 2 times 1 plus I, and times the arc tangent of I times e to the negative pi over 2, and minus image, right? Okay, so now if we look at here, this is what we have like concluded to, and now we are just going to copy this stuff down. And again, another thing, if you want these three things to be proven by me, just write in the comment section that Aman, prove all the three things that you used to prove this. I'll just make another video, and if you want, I'll make each like 3 videos separate to explain these three things. These are very necessary, I think, right? Okay, so s of half becomes 4g over pi minus 2 times of 1 plus I, and the arc tangent is being replaced with this I over 2 ln of 1 minus e to the minus pi over 2 over 1 plus e to the minus pi over 2. We're successfully getting rid of these two things. So s of half becomes 4g over pi minus of 1 plus I and times I ln of 1 minus e to the pi over 2 1 plus e to the negative pi. I'm just letting this I to be multiplied in these two stuffs to have two different terms. So s of half becomes 4g over pi. This becomes minus I times ln of 1 minus e to the minus pi over 2 over 1 plus e to the negative pi over 2. And this I times I is I squared. So minus times minus 1, I squared is minus 1. So minus times minus 1 is just positive. So this becomes positive of ln of 1 minus e to the minus pi over 2 over 1 plus e to the minus pi over 2. Okay, so now we are just going to take another step, and this is quite like okay, if I'm missing this imaginary part, let it be written over here, because in the next step we are just going to rid of all that. We are just going to get rid of all that stuff, like all the imaginary parts. And now I'm looking for the real part of s of half. So the real part, this is imaginary part vanished, this is imaginary part vanished, this thing and this thing is being carried out. So 4g over pi and plus ln of 1 minus e to the minus pi over 2 plus 1 over 1 plus e to the minus pi over 2. These things should be noted down, because now we have successfully calculated the real part s of half, and well, when lambda is 8i, right? And now onwards we are just going to move on to this part. Oh, wait a second. So yeah, as earlier we took s of x like this. was the sum as n goes from 0 to infinity of -1 to the n times 2n plus 1 times log of it was 1 plus lambda x squared over 2n plus 1 whole squared. Okay, yeah, and now, like, we began all the stuffs with this only, right? So we are just going to move on to this again, right? Okay, so before anything else, let's substitute x equals half and lambda equals 8i. So this becomes s of half equals the sum as n goes from 0 to infinity of -1 to the n times 2n plus 1 and times logarithm of, when you plug lambda equals 8i and when you plug x equals 1 half, like half, so 8i over 4, that is 2i. So it just becomes 1 plus 2i over 2n plus 1 whole square, right? Yeah. And now, so let me tell you something. Out of these three tools, we have used this one and this one, and now it's time to use this one, right? How are we gonna use that? Let me erase that board. So yeah. I'm looking for this part. I'm looking for this logarithmic part. I'm not looking for anything like before this logarithm part. I'm just leaving for some time, but I'm looking for this part. So log of 1 plus 2i over 2n plus 1 whole square. From our formula, log of z equals ln of modulus of z plus I times argument of z. And if we take the real part of this equation, so this becomes the real part of log z equals, this argument becomes 0 because we are talking about the real part only. So this becomes ln of mod of z. And mod of z here is 1 plus 2i over 2n plus 1 whole square. So if we take the modulus of z, it becomes 1 squared plus 2 squared over 2n plus 1 whole square. So this comes out to be 1 plus 4 over 2n plus 1. Well, this was a square, right? That was already here, and we have to square this term. So this becomes 4, right? And yeah, so just plug it down over here. So this becomes the real part of log z, or log z equals ln of the square root of 1 plus 4 over 2n plus 1 to the 4. More precisely, its real part of log z is 1 over 2 of ln of 1 plus 4 over 2n plus 1 to the 4. Yeah. Okay. So like this, the real part of this logarithmic term comes out with this thing, and now we're just going to replace it with that. Let me just write it down over here. Okay, and now erasing this stuff. So or s of half, or maybe taking the real part, because then only we can take the real part of this also. So the real part of s of half becomes the series as n goes from 0 to infinity of -1 to the n times 2n plus 1 times the ln, well, half ln of 1 plus 4 over 2n plus 1 to the 4th. This half comes out of the summation, so this becomes the real part of s of half comes out to be 1 over 2 times the series ln 1 plus 4 over 2n plus 1 to the 4th. Okay, and now like this is, we can write this whole thing as like this, the real part of s of half using the logarithmic property. Ln of 1 plus 4 over 2n plus 1 to the 4th whole to the -1 to the n times 2n plus 1. Yeah, we can write it down like that. And now we're just going to convert it into product. How are we gonna do that? Just take out this logarithm out of this infinite series, and then only it becomes the infinite product. Let's just dive into this board, and maybe this is going to be the last board we are switching up for. Oh, wait a second, I have to remember that we have calculated that as yeah. So rather than that, let's erase all the stuffs. So real part of this becomes 1 over 2 ln of the product as n goes from 0 to infinity of 1 plus 4 over 2n plus 1 to the 4th whole to the -1 to the n times 2n plus 1. Okay, and now we can compare these two equations, right? So this becomes 1 over 2 ln the product as n goes from 0 to infinity of the same stuffs, that is 4g over pi plus ln of 1 minus e to the negative pi over 2 over 1 plus e to the negative pi over 2. No, it's not gonna be ended on this board only. We are just going to take another that board, and now just multiplying this to both sides. So this is going to be vanished. So I'm just going to multiply this. So this becomes 8, and this becomes 2, here 2, right? So instead of writing here 2, I can write it down like this. I hope guys, there isn't any kind of issue that I jumped off, I think, one step. So yeah, I'll just multiply to both the sides. So this becomes like this vanished, this half, and here it becomes 8, and here 2 times ln of that argument, so it becomes ln of that argument whole square, right? And now for ln, we can take both sides to just neutralize this ln. So this becomes the product as n goes from 0 to infinity of 1 plus 4 over 2n plus 1 to the 4th of whole to the -1 to the n times 2n plus 1 equals e to the 8z over pi, and times e to the, or maybe I hope you guys know, like e to the ln is just the argument, like just taking out the argument in the base. So this becomes 1 minus e to the pi over 2 and 1 plus e to the minus pi over 2 whole squared. So that is what this infinite product evaluates to, and keep remember guys, this is what we thought we have to evaluate for. Let me just write it down for you guys over on this board. And again, if you have any sort of doubt in any step, in any kind of step, you are free to ask it in comment section. Just use the timestamp and let me know where you are having doubt. I'll make sure that I'll clear your doubts. So I'm just repeating that step. So this is the product as n goes from 0 to infinity of 1 plus 4 over 2n plus 1 to the 4th whole to the negative 1 to the n times 2n plus 1. So this comes out to be e to the 8g over pi times 1 minus e to the minus pi over 2 plus over 1 plus e to the minus pi over 2 whole squared, where g is Catalan's constant. Okay, so yeah guys, successfully we did that. It was quite lengthy, I know that, but yeah, I had a lot of fun in doing this problem, in solving this problem, and I hope that you guys also had some sort of problem, some sort of fun, right? And yeah guys, thank you so much for watching this video, and if you have any kind of doubt, free to ask in comment section. And yeah, that's it. Okay, let's meet up in the next video. So far, please take care of yourself and just study mathematics because it's love. Thank you so much guys watching this video. Stay tuned.